Okay, part C. Suppose that z equals negative root 12 minus 2i. Okay, how do we do this? Express z in exponential form. So better students worked out what the modulus was by just doing that Pythagoras there, and then you could work out the argument independently by taking your cos and your sine and then working out what the relevant angle was. Now it was really sad that unfortunately a lot of people tripped up at that step with working out the argument, perhaps because you went straight to using tan. If you have a think about it this way, when you do sine over cos, I might just write this up here in red, sine over cos is just going to give you, remember, negative a half divided by negative root 3 on 2. What happens there? Well, your 2's are going to cancel and your negatives are going to cancel, which gives you 1 on root 3. And so if you go to your calculator and you do tan inverse of this, because this is sine theta on cos theta, so this is tan theta, so to get theta you take tan inverse, right? But we caution you about this method right at the very beginning, right? You can see that this doesn't include the fact, because we cancelled it, that actually both of these are negative, right? The negatives have just cancelled. So if you do tan inverse of 1 on root 3, your calculator will hand you back pi on 6, or indeed 30 degrees if you're in degrees mode, and that is definitely not the angle. You can tell just by thinking about this. Draw yourself a basic diagram. This is in the third quadrant. There's no way that pi on 6, which is a first quadrant, that's an acute angle, there's no way pi on 6 can be the correct argument. So that's how I got a negative 5 pi on 6. Hence, evaluate the modulus of 1 on z and the principal argument of 1 on z. So you can see here what I did was I hijacked the fact that I had done the part 1 in exponential form. So 1 over z is z to the power of negative 1. And that's why you can see here I've got, this is the modulus 4 to the power of negative 1, it's a reciprocal, a quarter. And then with my argument over here, because it was negative 5 pi on 6, when you raise that to the power of negative 1, the negatives cancel, so that gives you 5 pi on 6, and that's it. No more having to go back into polar form or doing any other working. You've already done enough in part 1 to get you the solution in part 2 without too much work. So we'll pause here and point out that even though this is only question 4, part C, several of you were already taking a lot of extra time, and this only got worse as you got further into the paper, by using inefficient methods or putting a lot of additional working or not drawing a diagram, which made things just a lot harder for yourself. So that's where you sort of cost yourself time, and when you went further and further into the paper, you found you didn't have enough time for later questions because you had sacrificed that time in the earlier ones. Okay, we're up to part D now. So by writing the number I in exponential form with its principal argument, show that I to the I is a real number. That's what that weird notation means, okay? So let's have a look at my solution over here. You can see that over here I have written I first in polar form just to make it really obvious what's going on here, right? You can see that this cos of pi on 2 is 0 and then sine of pi on 2 is 1. So 0 plus a single I, that's what gives you I, and that's how I've written it in exponential form, and pi on 2 is the principal argument as the question has requested. Now the reason why this is useful is because to get to I to the ith power, you can then just raise both sides to the power of I. And because this is written in exponential form, you just get I squared at the front by multiplying those indices. I squared is negative 1. This is a real number. This is a real number. You just got a real number. That's it. So you didn't need to think too hard. Again, this is a place where students spent a lot of time. You might have, converted into some other form and sacrificed a lot of the time that would have been useful later in the paper. This is all you needed to do the question. And by the way, this result here is, just as an aside, is a bit of an Easter egg here, because I think it is just weird and delightful that I to the power of I is equal to a completely real number. Only imaginary stuff mixed together and you get only real stuff. I should point out there is a minor caution here, which is that I to the I can equal other real numbers, and that's because you can you don't just have to express I with its principal argument. You could have chosen a different argument if the question hadn't specified, and you would have gotten a different number at the end. But importantly, it still would have been real, which is part of why I phrased the question in an unusual way that I did. Okay, we are on the last part of question 4 now. So this is a proof. It says if z equals sine alpha plus I cos alpha, show that, and then you've got this equation over here on the right hand side. So how do I make this work? Well, as in all cases, you need to pick for your result over here, you need to pick a left-hand side or right-hand side to start with, and then move over to the other side, whichever direction you're going. And I think most people are pretty happy to start with the right-hand side because it looks like a mess, and then move over to the left-hand side. So there are a couple of different ways you can do this. Firstly, you can use some of your properties of the conjugates, the complex conjugates of complex numbers, but you do have to be careful when you use these results in a proof. You really, the burden of proof is on you. You've really got to show why these things are true. So let's have a go at this using conjugate properties, which is probably the fastest way. Okay. For starters, I start with this. This is just me quoting the right-hand side, and then what I do is I multiply by z over z. Now this is a bit unusual because you might think, well, how is this going to simplify things? On this first line here, not much is simplified at all. You've got the z outside of the 1 plus z. You'll see why I didn't expand that in a second. And then on the denominator, you get z plus z, z bar. But some of you might remember that z bar actually is a useful sort of result that you've seen before. We've actually proven this result in class, but I wanted to prove this, right? You can't just sort of pluck this out of nowhere, and you have to do this correctly. And those of you who took shortcuts around trying to use this result, but didn't actually prove it, some of you got it wrong because you didn't prove it, so you tried to rely on your memory. This is not on the reference sheet or anything like that. So this is me multiplying a number by its conjugate. You can see you just get this. This is just the expansion, but you've got these ixy's, which are they're the imaginary parts, right? You can see they cancel, plus and minus. Just leaves you with x squared plus y squared, and that is, since the modulus of a complex number is the square root of x squared plus y squared, that's why you've got the square of the modulus. So that's why you can see me taking that idea and substituting it in here. So in this case, I actually know what the modulus of z is because I get told that z is not just any number, it's sine alpha plus I cos alpha. That might have weirded you out a little bit because the sine and the cos are reversed from what you would normally expect, but this is still, importantly, a number on the unit circle. It's just not where you would normally expect it to be. So when you find its modulus, sine squared plus cos squared, that's 1. So this is nice because on the denominator you get z plus 1. This 1 plus z is the same as z plus 1. So those two cancel. That gives you z as required. Now this is a really clever way of doing it if you are new to use that conjugate property, but a lot of you might have said, oh, how did you think of that, right? Like maybe this result here, z bar equals the modulus of z squared, didn't immediately rise to your brain, and that's fine. There is a second method. It's a bit longer, but it works just fine. What I'm going to do is turn everything into polar form, use my trigonometric equations and identities to be able to handle this. So you can see this is me rewriting the result that was required to be proven. Z equals 1 plus z on 1 plus z bar. So you can see there's z and there's z bar. So I've just taken that, I've written it over here, this is my right hand side, and then I'm multiplying by, this is the conjugate over the conjugate of the denominator. Can you see that? You can see there's the plus I cos alpha, which is the opposite side to the minus I cos alpha. You're going to get difference of squares down here, and even though that's going to give us a bit of a mess, we can still work with it. And you can see I'm basically just expanding left, right, and center. What's great about this is because it does look like a mess, I can actually do a lot of simplification because you can see on the denominator, for instance, here, you've got a sine squared plus cos squared. That appears, which is the Pythagorean identity, that's equal to 1. And so you can see that this one and this one collect into this 2, and you get a similar situation happening on the numerator as well. You get all of this cancelling happening. You can see that I've got, let's have a look at it, this term here, this comes from the square of this term over here, but because I want to get everything sort of cancelling out with each other, and I've got this, I notice a sine squared minus cos squared, I turn the cos squared, again using the Pythagorean identity, I turn that minus cos squared into minus 1 minus sine squared, right? So that allows me to collect like terms with these sine squareds, and you can see me then getting to this point where I can factorize and pull out the 1 plus sine alpha, which I also factorize on the denominator. Because remember, I know I'm heading towards z. If I've said it once, I'll say it 100 times. You need to not just have an eye on what you're proving, but also on your destination, what you're trying to get to. And so I know the denominator needs to cancel out. There is no denominator in this result over here, the left-hand side that I'm trying to get to. So that's why why I kind of had faith that this 2 plus 2 sine alpha was somehow going to cancel, which indeed it does once you get to your final line.